To Congress, or actually not the Congress, the Supreme Court decided that military technology is cutting edge, and so there's always a hazard, and you cannot sue the manufacturer for a design defect because the military is considered to be the designer of every piece of military hardware. Okay, and it's called, what do they call this this principle? I can't remember. But anyway, in 1992, the Supreme Court ruled that you can't sue Pratt & Whitney for an engine design defect. You can sue them for a manufacturing defect, but you can't sue them for a design defect because NavAir or the Air Force had huge design teams of all these PhD scientists who work for the government, and Pratt & Whitney would come in and they would give a presentation, or Boeing if it's an aircraft airframe. They would give a presentation to the government, and the government would approve it, and so therefore the government approved the design. And you can't sue the government. I mean, when you signed up for hazardous duty, right? So that's not to say you can't get something. I worked on the V-22 Osprey that crashed at Quonset. Quonset. Wasn't Quonset. Quantico, Virginia, Ship 4, and there were 4, let me get this right, 4 military on there and a bunch of civilians. If I remember, Boeing and Bell settled, with the military people right away, but the civilians all filed suit. Anyway, it's a mess, but they finally, it went to trial and stuff, but we can talk about that some other time. Okay, it doesn't have to do with corrosion. So that was one of the things I was going to say. Just make sure you understand that as military officers, your lives are worthless. Okay? At least from a business point of view. But you can eject, and if you survive the ejection, you're fine. Okay?
Well, like you said, planes are expensive, so I'm just surprised that they would even consider like a single engine fighter jet plane when the planes are really expensive.
Well, but the engines are about, depending on the aircraft, well, in a military jet, the engines are probably more than 50% of the cost of the plane, okay? In a commercial jet, it's probably 20-25% of the overall acquisition of the aircraft. Is well, it depends on the aircraft too, but the engine is going to go for 5 or 10 million on a 747 now, or something like that. And the nacelle, that holds the engine on, that goes for 5 million. So if you got 4 engines, there's $60 million. That's not 50%, but on 747, which costs about 200 million, you're talking a third of the cost, roughly. So on a military jet, the engines actually go for even more. One of the problems, and this is really getting into a digression from corrosion, is about 20 or 30 years ago, development of military jet engines and development of commercial engines diverged. Anybody know why? Because they were looking for fuel efficiency in the commercial area because, well, on some of the other lectures you might get some of this, but a 50-degree Fahrenheit increase in the operating temperature of a commercial jet engine will save just U.S. airlines $50 billion a year in fuel. Okay, that's a lot of money. And that's why they're always talking about fuel economy, and they retire aircraft when they retire the engines, and they're always looking for the latest engines which are more fuel efficient. Well, the problem is, in order to get a high fuel efficiency, they decided to go to what's called the high bypass jet engine. I mean, this has nothing to do with corrosion, but that's okay. It's interesting. So, there's 2 equations, 1/2 mv squared, and then there's the momentum equation, mv, right? And so if I have a jet engine, the old jet engines, which are still the military engines, were just a long tube, and whatever came in was a certain amount of mass, went out the back as a certain amount of mass, only it had a lot bigger velocity, right? So a lot more energy, and the energy came from burning the fuel in here, but the actual thrust to weight ratio and stuff is momentum. And so the problem with momentum is you didn't have a lot of mass going through this little tube. So they came up with a high bypass, and they put these big fans around here, and you see this if you go flying a commercial jet. You see these engines that are, 10 feet in diameter, right? Well, the basic core engine still is this, but you also have the engine is now driving these fans, which are pulling another mass, a bigger mass, and you get this m little v. So you get lots of high velocity with a little m, but you get lots of mass with a little v by the fans, and now you get a tremendous amount of thrust and tremendous efficiency. The problem is you can't do this with a supersonic engine, and the military engines want to go above the speed of sound, okay? Commercial engines don't want to go above the speed of sound. So the military engines still are basically the core. They're inherently fuel inefficient, okay? Because they want to break the sound barrier. So what's the solution to all of this? Well, it turns out the other solution to all of this, you can't run modern engines without a computer. I mean, the computer is basically changing parameters in that engine 1,000 times a second or faster. The airfoils that control a modern military aircraft, in order to get the maneuverability, I mean, when you're going Mach 1.5 and you want to take a right turn, you can't do, no human could respond to all the control surfaces, and so you have computers running those control surfaces. And a lot of the plane designs now are inherently unstable, just like a submarine going through the water. And we won't talk about the fact that the deeper you are, the slower you have to go, because if you go unstable and you go deeper than you're supposed to go, it's not a good thing in a submarine. Well, the same thing in a jet engine. If all of a sudden one of the control surfaces sends you in another direction you didn't want to go, it's not a good thing when you're going Mach 1.5 and you take a 90-degree turn. The G-forces were such that the pilot will pass out, okay? And in fact, that's one of the problems. The F-22 and the F-35 can do maneuvers that the pilot cannot take. Above about 8 or 9 Gs, the blood doesn't get to the brain anymore, okay? You get to the point where the heart is not strong enough to pump it. Anyway, because of that, the solution is drones, pilotless aircraft, which should be one of the solutions for the Navy, to think of ships without people. I'm sure they are. Well, you have underwater autonomous vehicles, but I mean, do you realize what it costs to build a submarine or a surface ship that has to accommodate all these people and their dietary needs and their other needs to take showers and drink water and things like that? If you take the people off the air, and not only that, they won't die. I mean, those people in Tampa that are fighting the war in Afghanistan, they go home, at regular time, and someone else takes over. These other guys marching through Afghanistan, that's not fun at all. But in Tampa, it's not so bad. Okay, so maybe we ought to go ahead and start. Anybody have any questions on that? I mean, some of this technology is actually pretty neat. But that's another one of my lectures. Is one of the problems nowadays. It's not a lecture, regular lecture. One of my diversions is the problems with war. I mean, the one war that wiped out more, I don't know if it wiped out more, but probably more of the population of the country than virtually any other war was the U.S. Civil War. I mean, we were killing each other, and we did it very effectively. I mean, if you got wounded, you were a dead man. I mean, medicine couldn't survive. You just bleed to death, okay? And then World War I was the war to end all wars, and World War II. But as we've gone along, casualties have become less and less acceptable. When I was actually younger than you, it was the Vietnam War, and they would publish the body count every day, okay, and every week, the front page of the paper. And it'd be like 100 soldiers a day, dying in Vietnam. Well, now we've gotten to the point where, by the time of the Gulf War, we got to the point where it's unacceptable to have U.S. casualties. And now we get to Afghanistan, and it's unacceptable to have the enemy casualties. Wait a second, what is war about? Okay, anyway, you know what Clausewitz said, right? War is extension of politics by other means. But anyway, that's, see, I did take ROTC, okay. That's where I learned some of these things about the philosophy of war. It's best not to fight wars. It's cheaper too. Okay, we can go on if you want. Are we on? Okay. Turns out I just happened to get this book. It arrived after class yesterday on cathodic protection. I'm sure you all are busy purchasing books like this. But it says that I told you about the cost of corrosion. And it says in the first study was done in 1976, and they found that it cost the U.S. $70 billion loss in 1976. And this was somewhere between 3.5% and 4.5% of the country's gross national product. They redid the study in 1982, and it was 126 billion. So it went from 70 to 126 billion a year. By 1991, it was 276 billion. If you actually calculate that, that's higher than the inflation rate. What it is lies, damned lies, and statistics. They were including other things. For example, in this, they assumed that every automobile that's junked is junked because of corrosion. That's not necessarily true. A lot of them are junked because of a crash. They're totaled in a crash. That's not corrosion. However, they've done two studies, one by NIST and one by the National Association of Corrosion Engineers, and they both came up with corrosion cost about 4.2 to 4.9%, plus or minus 30% statistics of the gross national product. If it is about 5% of the gross national product, what's that today? Anybody know what the gross national product is today? It's about 15 trillion. So 5% of that is 750 billion. Now, do you believe that? That that's the cost of corrosion? Neither do I, okay? But that's what the National Association of Corrosion Engineers will tell you, okay? And I'm sure they have all the data but they will do whatever they do to inflate the numbers because it's in their best interest. But corrosion does cost a lot of money, and if you could stop it. But in fact, the main principle, metals don't want to be metals by nature, and so they will go back to their original state over time, and the way they do it is by corroding. Corrosion, if you look in the dictionary, is the chemical degradation. Corrosion is a slow chemical process, or a corrosion engineer is the degradation over time of metals. Now, then you get into questions like 3 Mile Island, the sister reactor at 3 Mile Island. When they wanted to restart that nuclear reactor, they started up the steam generator, and there's a type of acid that you can only produce. You can't produce regularly in the laboratory, but under the high pressures and the startup temperatures, you can generate, and you have some sulfur contamination, you get polythionic acid. It's a polymerized sulfur compound, and this nickel-based superalloy heat exchanger on reactor 2, not the one that had all the problems, but they were trying to restart it so it could generate electricity a couple of years after 3 Mile Island. They started it up, and within a half an hour, they had stress corrosion cracks, and it cost them $30 million to repair, okay? Well, the fundamental question there for the insurance carriers was, if all the damage was done in a half an hour, was that a slow process? Was that corrosion? Okay. The first press releases to come out of 3 Mile Island from GPU Nuclear, which was the utility, the first day and a half, they called it stress corrosion cracking, SCC. By the time the attorneys had gotten hold of it, they called it stress-assisted cracking, because the attorneys went and looked at their insurance contract, which excluded corrosion. Because corrosion is just a slow, gradual wearing away, and they knew that if they called it stress corrosion cracking, the insurance company was going to deny the $30 million claim. If they could change the name and call it stress-assisted cracking. Well, what cracking is not stress-assisted? Okay? But I mean, you start getting into, this is when we get into the story about lawyers, okay? You can go back to the Bible and see what the Bible says about lawyers. But in any case, that's what they do. The second point from yesterday, metals may possess immunity, or we called it nobility. or they can have practical nobility, which means they've got a coating of some sort of protective oxide or something else. And to give you an example of something that has a protective oxide, anybody know what this is? Some of you must be mechanical engineers. You should call this a pipe nipple, okay? It's threaded on both ends. Bought it at Home Depot, cost me like $1, okay? 3/4 inch by 6 black nipple. Why is it a black nipple? Because it's got a coating of Fe3O4 magnetite on the surface. When you heat up steel to above about 500 or 600 degrees Fahrenheit, and this thing gets to temperatures of 800 or 900 degrees when they're forming it in the steel mill, it will form not Fe2O3, which you know as rust. It will form Fe3O4, which is called magnetite. Okay, it's slightly magnetic. You ever play that little game with the magnets where you put the mustaches and the beards on this little figures? You know, that's magnetite. That's another use for magnetite. But in fact, the black iron pipe has its own magnetic, or not magnetic, it has its own inherent coating. Okay, if you go down to the basement of MIT and you look up, you'll see the fire sprinkler system, and it's black iron pipe. You can tell it's a fire sprinkler system because the couplings are either orange or red, right? You've seen these Victolic type couplings that have gaskets. You probably have something similar types of things on board ship. Okay, and it's black iron pipe. They don't do anything other than just take the regular mill finish, although this one someone put varnish on. Which doesn't hurt it, but anyway, and that keeps it from corroding. How come rust is not protective? Fe2O3.
Because it can be easily flakes off.
Right, it flakes off. It's flaky. Rust is flaky. So it turns out if you can keep a protective coating on something, you can actually get pretty good protection. This comes out of one of these marine books that I showed you yesterday, and it shows you what happens to the corrosion rate in millimeters per year versus exposure time in days. So a year is right about in here. And if you have attached rust, the corrosion rate in millimeters per year is something on the order of 1/10 of a millimeter per year. What's that in inches? You're Canadian, you know the metric system. Okay, a millimeter is 40,000ths of an inch, so 1/10 of a millimeter is 4,000ths of an inch. I did that calculation in my head, okay? And that is the typical corrosion rate for steel in the atmosphere or in lots of other humid or moist environments. This happens to be seawater, and it was probably painted, okay? But where the paint was worn away and stuff, it did rust. And it was rusting at about 4,000ths of an inch per year. That is a good general rule of thumb for the corrosion rate of steel in water. Okay? If the numbers I use are typically 002 to 010 inches. Oops, 010 per year. 2 to 10,000ths of an inch per year. So sometimes people come to me and say, oh, we had this piece of black iron pipe, which is about 1/8 of an inch thick, and it corroded through in 1 year. And I said, no, it didn't. Okay? It should last 10 years, even in a very severe 10,000ths of an inch. And at 4,000ths of an inch per year, it should last about 25 years. And those of you who have been aboard ship and you have carbon steel piping, how long does it last? About 25 or 30 years before you really need to sort of get rid of the whole thing. And that used to be the limiting lifetime on ships. Okay? But then someone at NAVC said, oh, we need ships that will last 50 years, right? Because we can't afford to replace them so often. So I'm not sure if the person understood that what happens to carbon steel, but eventually they learned that the carbon steel is worn out after 25 or 30 years. And so they replaced it with, you've been to the shipyards. What types of metals are they replacing the carbon steel piping with?
Aluminum.
They might be on some of the modern ships that are mostly aluminum ships. Aluminum actually is what we build most sewage treatment plants out of. Okay, so aluminum actually has very good long-term corrosion resistance in not so good water. But on nuclear subs, they first went to cupro nickel, Monel, now they're into titanium.
Depends on what.
Depends on what the piping system is, I know. What?
I don't think
What? You don't think what?
well, there are, at least, since, in my experience in submarines, if the system is built one way, it's pretty much going to stay that way. I know, like, some of the seawater systems have gone titanium with some of the, kind of more specialized boats, but that's.
Well, they are using a lot more titanium than they were 40 years ago, believe me. I mean, 40 years ago, they just assumed you scrap the ship after 30 years. And they would go with the lowest cost, which was carbon steel. Now, and actually, it's true, even on subs and critical systems, like the reactor systems and stuff, they would use cupro nickel or a Monel in critical systems. But there's a lot more titanium in piping now than there used to be, okay? There was no titanium 20 years ago in piping on ship in general. But the problem is, and you all know the problem is, titanium is, as fabricated, you don't have to use something as thick if you don't need the pressure, but the cost is still a factor of 10, 20, or 30 times carbon steel.
We saw in one of your slides yesterday that sewage systems are very susceptible to corrosion.
Yep.
So how come we don't use like plastic piping on ship or something for that?
Well, there's a couple of reasons about plastic piping. Can I hold that just a second until I finish? Let me just finish this. This is, if you look at the top of this is up in the shear strike region, the top part of the ship where it's bowing from bending, and the rust is flaking off, okay? And it's the detachment of the partially protective rust. Okay, so why haven't we switched to plastic? We have been switching to plastic. It turns out plastics are sort of a recent development, okay? The history of polyethylene, which is one of our most common plastics and one of our cheapest plastics, is polyethylene really didn't exist in World War II. I mean, they knew about it, but it wasn't a commercial development. In the 1950s, I can't remember which big plastics company, what is now a big plastics company, built a plant that they decided they were going to be able to produce hundreds of millions of pounds of plastic polyethylene every year. And they started producing it, but they didn't really have a market. And their original quality of manufacturing of this was sort of variable. And so they tried to take it into somebody and say, oh, why don't you use this for plastic pipe or whatever the application was. Because it's easy to extrude, you form everything at temperatures you hardly burn yourself in the plant because everything's low temperature. Well, it turns out they were just all the production trials they were running, they couldn't sell their junk because it had no consistency. They hadn't come down the learning curve of manufacturing to get consistent quality. And then a magic thing happened. Someone thought of an application for all these 50 million pounds of scrap polyethylene that was sitting there, and it was called the hula hoop. Okay? It had no real requirements other than it be a round tube, and it could be made in different colors and stuff. And in the 1950s, the hula hoop became the big craze. Anybody ever used a hula hoop? Okay. Well, all of a sudden, they were able to sell their 50 million pounds of polyethylene and start producing more polyethylene, and over time they learned to make it a better quality. Okay, the problem, and I went looking this morning for a piece of polyethylene, actually a special type of polyethylene. Problem with polyethylene is at about 140 or 150 degrees Fahrenheit, it will creep, it will bulge, it will get an aneurysm, and it will explode on you, or it'll burst, and you'll have a flood. So people tried better things like polybutylene, okay, longer chain hydrocarbon, and they put that in lots of houses. Anybody ever have a house that had polybutylene fittings? Yeah, what happened?
Oh, nothing yet.
Oh.
It's still holding up. But yeah, they have a tendency for that.
Yeah.
PEX stuff is made out of?
No, PEX is cross-linked polyethylene. I'll talk about that in a second. That was what I was looking for, is a piece of PEX. What? Well, PEX actually, The PEX tubing is fine. Some people are blaming the fittings. There's $1 billion worth of lawsuits out in Las Vegas and the West Coast on PEX fittings, brass fittings. But that's another story. Which is a corrosion problem called dealloying. Maybe we'll talk about it when we get there to dealloying type of attack. But so anyway, they put in polybutylene, and the fittings are susceptible to stress corrosion cracking. So I talked about metals are, energetically unfavorable. They want to go back to nature. And then it turns out, if I went back 30, 40 years ago, people said, oh, well, plastics don't corrode. And they said, ceramics don't corrode. Well, that's not true. They corrode by different mechanism. Metals corrode by going back to their oxide or their sulfide. Plastics can degrade, and this is not necessarily by a chemical process. So maybe the corrosion engineers were right as they started getting into the degradation of these other materials. You can have separation, you can have cracking. The polybutylene fittings started cracking. People had mold growing in their walls because they'd start leaking. I had a daughter who about 1998 bought a condo down in Raleigh, North Carolina, and it had polybutylene, and she knew about it, and she got in just under the wire of the class action suit, and they paid her $2,500 to have all the fittings replaced. Okay? So, I mean, it's not the end of the world, but they don't use polybutylene because it stress corrosion cracks in certain types of water. One of the best stories about plastics corroding was DuPont came out with something called Delrin, which was you can call it polyformaldehyde, it's called acetal, but basically it's polyformaldehyde. Formaldehyde is one of the simplest hydrocarbons, okay? What is it, CH2O or something? I think that's formaldehyde. You can Google it. But I think it's a CH2O. And if you polymerize this, you can make a 10,000 psi plastic, which is very strong, easy to injection mold. And DuPont came out with a paper in like 1958 that tested this polyformaldehyde in 200 different solvents, and it was resistant to all these chemicals, and this was the plumbing material of the future. In 1962, some Germans did a study and showed that over the long haul, at the types of stresses you had, you would get a form of stress corrosion cracking in polyformaldehyde with small amounts of chlorine. Okay? So about 15 or 20 years later, Celanese, we know, paid a $900 million class action lawsuit to take Delrin out or to pay for all the Delrin failures. Well, they didn't call it Delrin, they called it, their trade name was different. DuPont paid an even bigger settlement, well over $1 billion, but it's confidential how much they paid in their settlement for Delrin, okay? Now, it turns out Delrin, the problem with Delrin is a little bit of chlorine. Now, how much chlorine? 10 years ago, if you went to the DuPont website and it listed the materials that it was resistant to, and oh, by the way, the 1958 paper, the one solvent that they didn't test this material in was water. They actually never tested it in water. So you look at all these organics and stuff, they just never bought. This was the plumbing material of the future, and they figured the water wouldn't corrode it. 10 years ago, you went to the DuPont website and you looked at Delrin and it said water and it said corrosion resistant, and it had no asterisk, and it said with less than half part per million. Now, how much, you want to make coffee out of the Cambridge water this morning? How much chlorine's in the Cambridge water? Anybody have an idea?
How much more do they have?
Well, it's basically rainwater, but it comes out of fresh pond up here since the 1640s, and it has 5 or 10% chlorine. So if you have water that's cleaner, 10 times cleaner than what you get out of the streams and brooks, but really good water in the Northeast will be 5 or 10 ppm chlorine, and DuPont's it's corrosion resistant, something that's 10 times better than some of the better potable water. The EPA says you can have up to 100 parts per million chlorine and it's still potable water. So if you're in San Antonio or Las Vegas or something, you could have 70, 80, 90 parts per million chlorine. Delrin's not so good, okay? Well, what did they make out of Delrin? They had the little water closet valves. You know, you flush the toilet and you know, it fills up with the float and everything, and then it shuts off. Well, they were making those things out of Delrin. And after about 2 or 3 years, the chlorine in the water would cause the Delrin just to turn into a brittle, just full of little cracks. And they had what they called the exploding toilets, okay? Because when this thing would let go, the 60 psi water pressure would hit the little ceramic top to your water closet, and it would go, you know, you'd hear it blow off. It wasn't really an explosion. It wasn't a release of gas pressure. It was water pressure knocked the top off, and it was ceramic. It fell to the ground. You hear the crash of the breaking top, and then you have a flood in your home. And people would be in their home, and they'd hear this loud noise, which they called an explosion. And so you had what they called exploding toilets back in the 1980s from Delrin. Okay, so plastics do corrode. Many times in very subtle ways. Some plastics will stress corrosion, crack in very clean water, nearly pure water. Okay, water can attack the plastics. Same thing with ceramics. Ceramics, they often want to use ceramics at very high temperatures, like in some engine part or something. Well, sulfur compounds just destroy ceramics in general. Okay. So these other things do corrode. They maybe they environmentally degrade rather than corrode. But why don't they use it? Now the PEX. PEX is cross-linked polyethylene. And there are 2 types of PEX. There's PEX A and PEX B. Isn't that a clever way to call it? So PEX A, PEX B is electron beam polymerized. Okay? Remember Charles Goodyear and sulfur and putting it in latex and making rubber? Okay? You know, that's how he learned how to make rubber, you know, in the 1830s or whatever, by putting some sulfur in with the latex, and the sulfur would create cross links between the long polymer chains. I'm not getting a lot of nods here of remembering Charles, okay? Well, it turns out Charles Goodyear, I guess, got a patent on it, but that's because he didn't know that the ancient Mayans or whatever actually used to use the, it's a vine that had natural sulfur compounds, and they would mix that. And so their ball, remember they used to play this, what do they call it? What was the game they played that was over miles and miles with this rubber ball and things down there? Anyway, Mike Tarkanian, who runs the lab over here, for his bachelor's thesis was the one who rediscovered the fact that the Mayans from thousands of years ago used the morning glory vine, a type of morning glory that had natural sulfur compounds. They mix it with the rubber and they get cross-linking. Well, you got these polymer chains, which in polyethylene is basically just C with a bunch of H's. So you've got a backbone of carbon, and it could be 10,000 carbons long with hydrogen, and then at the end you have to have another hydrogen. But in fact, so we got hydrogen. It's just a chain of it's actually CNH2N plus 2. Okay? So for every carbon you got 2 hydrogens, and you have to have a hydrogen on the ends, both ends, so it's 2N plus 2. That's the formula for polyethylene. Has the exact same formula as paraffin, wax. And so one way to tell if something is polyethylene is you just take a little piece of it, you burn it, and see if it smells like a candle. Okay? This is actually one of the scientific tests for polyethylene. You need to understand these sophisticated tests we use in the world. Anyway, PEX A, they basically get cross-linking by hitting it with an electron beam, which breaks some of these bonds, and you can actually get links, and now you have a carbon coming off this way, and this way, and this way. Well, you can't have that. Anyway, you can only have 2 carbons at a time. But you can have cross-links with carbon, and you get the same type of thing as taking latex and vulcanizing it and making rubber. Okay, so they can do it with an electron beam, or they can do it chemically, where they add compounds And the chemical compounds help break down some of the polymer chains. Here they're just using a lot of energy to break the polymer chain and hope that it reforms, and it does. This is made by a company called Uponor. This is made by almost everybody else. And now you have enough strength in all directions, and these things don't just burst on you. So the best anyone knows on the PEX, which has been in service for about 25 years now, and it shows no evidence of deterioration, the PEX will probably last about 100 years, okay, or more, okay, but the best estimate right now. But the people are complaining about the brass fittings, but we'll talk about that when we get to de-alloying.
It's convenient because you can run one long piece of tubing and put all the fittings in place. It's not going to matter if you don't use it.
Well, in fact, that's why people like it, because A, you don't have to use much copper. I mentioned yesterday, some people are tearing the copper out of their homes to sell the copper and putting PEX back in, okay? So they're taking the investment value in their home, the copper pipes, and replacing it with PEX. The problem is some attorneys in Las Vegas got about a $250 million settlement for corrosion of some of the brass fittings. And so now there's a feeding frenzy by attorneys claiming that this causes leaks, okay? Except no one's ever seen one of the leaks. But they corrode, and anyway, we'll talk about de-alloying later. They do get corrosion in Las Vegas water. Las Vegas water is not the best water in the world, okay? You can drink it, but it's not good for your pipes. But that's another story. Okay. So the point here is the scales can be protective. We sometimes put on artificial scales, which are called paint, okay, or galvanizing, which will try to protect things from corrosion for the general corrosion protection. Now the next thing about corrosion here, third point, is you need free oxygen or sulfur to get corrosion. Okay, that's the way it's found in nature, and if you're going to have a metal corrode, you need some free oxygen. Now, what do we do to prevent that? Or actually, let me put it this way: if I have black iron pipe, I can make my boiler system, my heating system in my home out of black